All right, here I am back again. This is Math 101 Coronavirus Edition. We are now going to look at the GCD of three numbers. GCD of three numbers. This is again some review from previous weeks, but I thought it would be a good idea to get us all back up to speed with this. So GCD of three numbers, we're going to take the GCD of 12, 18, and 30 for this exercise. And again, we're going to do this by four methods. So first method is list all divisors. Now for this example, I have already got lists of the divisors of 12. They are 1, 2, 3, 4, 6, and 12. And I've got all divisors of 18, 1, 2, 3, 6, 9, and 18. These are the divisors of 12 and 18 that I calculated in the previous video. So now we need divisors of 30. In order to do that, I am going to find the prime factorization of 30. 30 is 5 times 6. 5 is prime. I circle it. 6 is 2 times 3. Those are both primes. I circle them. So now I'm going to write the prime factorization of 30. There's 1, 2, there's 1, 3, and there's 1, 5. Now I'm going to now do tables to do all the divisors of 30. So my first tables are just going to use powers of 2 and powers of 3. So all the powers of 2 down the left side of the table, all the powers of 3 across the top, and there we go, 1, 2, 3, and 6. Now I haven't included any 5s in this first table, so I'm going to, as a reminder, put 5 to the power 0 at the bottom. I have no 5s in any element of the table. The next table I'm going to make is where I do include 1, 5. Otherwise, the table is going to be the same. Now, the second table, I just take everything in the first table and multiply by 5. So 1 times 5 is 5. 2 times 5 is 10. That's 10. I'll just clean that up a little bit. Okay. Sorry, 10. 3 times 5 is 15. 6 times 5 is 30. Finally, that gives me a list of all divisors of 30. 1, 2, 3, 5, 6, 10, 15, and 30 in order. There should be 8 of them. Let's double check. 2, 3, 4, 5, 6, 7, 8 divisors of 30. Correct. All right, so just copy my lists from above. 12 has divisors 1, 2, 3, 4, 6, and 12. And 18 has divisors 1, 2, 3, 6, 9, and 18. I look for common divisors. 1 is always going to be in all my lists. I'm going to underline it, but also 2 is in all my lists. 3 is in all my lists. 6 is in all my lists. 5 is not. 10 is not, 15 is not, 30 is not. So there's nothing else common to all these lists. So the greatest common divisor is 6 in this case. 12, 18, 30. The GCD of 12, 18, and 30 is 6. So 6 is the largest number that divides all of those listed numbers. All right. That's method 1. Method 2. We can accelerate this. Once we have the factorizations of 12, oops, 12 is, sorry, 3 to the power 2, 18, oh gosh, sorry, big mistake, erase all that stuff, that's just all wrong. All right, sorry about that, I got a little bit distracted there. Let's try it again. Using the factorizations of 12, 2 to the power 2 times 3 to the power 1. 18 is 2 to the power 1 times 3 to the power 2. And 30, which is 2 to the power 1 times 3 to the power 1 times 5 to the power 1. Just for consistency, I'm going to add a 5 column or 5 entry to each of these rows. There's no 5s in 12. There's no 5s in 18. There, so now we've got a nice kind of table, and we can easily calculate the GCD. As always, it's the minimum of these numbers. GCD includes 2 to the power 1 in the first column, 3 to the power 1 in the second column, and 5 to the power 0 in the third column. 5 to the power 0 is the minimum. 2 to the power 1 is 2, 3 to the power 1 is 3, 5 to the power 0 is 1, 2 times 3 times 1 is 6. So that gives us GCD by the second method. That saves us from making all of the tables of divisors, but it still requires us to do factor trees. If the factor trees are handy or if they're easy to do, this is a good method. But sometimes the factor trees are not available, so we're going to turn to the third method. We can use the Euclidean algorithm again. And we can do it by subtraction. So when you do it by subtraction, what I advise you to do is to take the second largest number from the largest number. So in this case, the largest number is 30, the second largest number is 18. 30 minus 18 is 12, and I replace 30 with 12. All right, now in this case, the second largest number is 12, the largest number is 18. I replace the largest number with the difference. Largest number is 18, difference is 6. Now, largest number is 12, second largest number is 6. Replace, excuse me, replace the largest number with the difference. Again, largest minus second largest. Replace largest with the difference. oops, 666. I don't know how that happened. And, oh, wow, what's going on here? I want you to go away. Okay, finally, let me see. Second largest and the largest are both the same in this case, so and one more time. Final answer is 6. So I knew that would be 6. When I reached this stage, I could have kind of stopped it there, but for completeness sake, I decided to do these last 2 steps. Now, there's a whole bunch of zeros here. There's a 0, there's a 0, and then there's a non-zero number, and whenever that happens, the GCD is that last non-zero number, 6. So that, again, gives us the same GCD of those 3 numbers, 12, 18, and 30, is 6 by, this time, Euclidean algorithm using subtraction. Finally, Euclidean algorithm, again, algorithm, we can use division. So GCD of 12, 18, and 30. Now, for division, Euclidean algorithm, what I recommend is you take the largest number and you divide by the smallest number. And that goes in twice, remainder of 6. I replace the largest number by the remainder. That is GCD of, there. Now, again, largest number divided by the smallest number, goes in 3 times. Remainder is 0. I replace the largest number with the remainder. So one more step, 12 divided by 6, goes in twice. Remainder is 0. I replace the large number with the remainder. And that gives me a GCD of 6. So we'll compare how many steps did it take us to do the subtraction method. Oops, that's not a step. It took us 1, 2, 3, 4 at least, 5, 6 if we're being very precise. Here I did 1, 2, 3 steps. So the Euclidean algorithm with division once again wins. It's at least as fast as the method with subtraction, and it will give us the correct GCD of 3 numbers. This works for 4 numbers, works for 5 numbers, works for any number, any size collection of numbers. I can do the GCD in these 4 different methods. Whichever method you choose is up to you on a test situation, but it's good to have a few different methods at your disposal. The first method is more for your understanding. It's not really a good way to calculate the GCD, but it helps you understand what it means. The tree method is great if you have trees available, and the Euclidean algorithm, either way, either division or subtraction, is useful in cases where you don't have factor trees available. All right, that's it for GCD of 3 numbers.